Welcome back everyone. So, we are studying topological phases of matter and we are in second chapter where now we are talking about quantum Hall effect. So, we looked at that quantum Hall effect. As you increase the magnetic field, we get to a region where we see that the resistivity or conductivity become completely quantized with only a fundamental constant E square by h is the proportionality constant to an integer. And that integer we found to be the number of Landau levels that are being filled at that magnetic field or at that chemical potential. Alright. So, then one may ask, like, Landau levels are flat and there is no dispersion in it. The way we approached it, we will add a dispersions into it once we talk about the TKNN invariant, but the way we approached it from a container model and making it a harmonic oscillator like theory, and then we obtain these energy levels which are completely flat. So, once a chemical potential is between the two Landau levels, it is an insulator, and that is what your resistivity also tells us, right. It is an insulator in this region. But how come we still have a transverse resistivity or conductivity? So, conductivity will also have the same feature, and that is something you can work it out from the tensor form of this conductivity, that when you have a finite transverse resistivity, you also have a finite transverse conductivity that is also quantized. So, how come the system is conducting electrons from one side to another side, despite the fact that it is an insulator? All the electrons have formed localized cyclotron orbit at the interior in the bulk, and the reason is that the conductivity is happening at the boundary, as we alluded, the skipping orbit concept. Okay. So, that means even the bulk is insulator, but your boundaries or edges are conducting. So, that is the metallic edge states. And then we will build on that to talk about that there is actually a charge that is being pulled from the bulk and send it to the edge by changing the magnetic field, or rather by changing the flux, which we saw earlier when we talked about the flux threaded through the solenoid and how the electrons are moving, and we will build on that and explain that as we change the magnetic field from each cyclotron orbit, there is some charge that is moving from the bulk to the edge, and that is how the current increases and the conductivity increases, and we will also touch upon the Laughlin argument. All right. So, the semi-classical picture is this. And we can actually solve it exactly by starting from a Schrodinger's equation and adding the magnetic field and also the electric field. But I will give you the solutions will look like, which I am going to draw schematically. This is my Hall bar, and we have all these cyclotron orbits. Threading some flux. And flux in this geometry we already talked about that they are like some monopole charge, magnetic charge if you like. But anyway, now as we have also given the voltage difference along x direction, so that means there is an electric field. So, what that electric field will do is that it will try to drift this orbital this way, and the holes, if there are also holes in the system which were going like this, and they will be drifted to this way. And as they drift here, they will come here, they will not be able to form a full cyclotron orbit anymore. So, they will go like this, and whereas this guy will go and now we will have a voltage difference between them, because there are now more electrons which have been pumped to this edge by taking electrons from this side. So, you are left with positive charges or holes. So, there is a electron flow that has happened which is opposite to the electric field, to the directions of the electric field, and here they have been moved from or pumped. And once they hit the edge, then they move along the edge. So, you get a metallic edge. Okay. So, the cyclotron orbit has been drifted or pumped, charge has been pumped to the edge by electric field, all right. But then those accumulated charge are now moving on the edge, or metallic edge is obtained by confining potential. Okay. So, what you can do is that you can go back to the Schrodinger's equation that we started with, then you can put the electric field or the potential due to electric field plus a confining potential equal to E. And what you will find? You can solve this. If you do not have these two potentials, you had Landau levels, and now what we will find is that these Landau levels will be tilted. Okay. And this is a homework for you to do. I had some chemical potential and I had these Landau levels, and these are the Landau levels which were empty, and I had some n number of Landau levels that was filled, and this is my energy. Without E and potential. Now we will add one by one, and this is again the chemical potential. So this Landau level will now, and here I am plotting as a function of x. So here is my boundary, this is my Lx, or rather Ly, I think, yes. Okay. So, we will see that as we go here, due to the confining potential, these Landau levels will have some, will bend. and it's kind of a airy potential that you can add to show this. Okay. And then even this one, so all of them. So each Landau label then has one metallic state. Right. And whereas these guys will also have the bending, but they will be unfilled, they are already above the Fermi label. So these Landau labels will now passing through the Fermi label, so it is a metallic one at the edge due to the confining potential. Now, because of the electric field, there will be a tilt, and from one side to another side, so this guy will be less filled and this side will be more. Okay. All right. So there will be then more electron in this side, sorry, the more electron in this side, and that electron has come from this side. Electrons has not been pumped from the outside, it is the same electron, but from one side through bulk it has gone to this side. And that is how there is a voltage difference between this side and that side that arises along the y directions, and that is the Hall voltage. Okay. And we see quantizations because it is only the number of channels, you know, each channel as you occupy you increase the conductivity by an integer value. All right, and now we will talk about how is this charge pumping that is related to flux quantizations and so on. So let us go back to some linear response theorem and our Ohm's law, in which the current along some I direction is related to electric field along j direction, and I and j I am assuming to be different. So, I am only interested in Hall current. Leverage beta. And that is my Hall conductivity, or rather if you like. Okay. So, let us start from this equation. How this current is related to the through continuity equation is related to the charge. So, what we are doing is that we are sort of creating a gradient of the current between the two between the two surface, and how would that correspond to change of the conductivity. So, continuity equation and use the and a summation symbol over the repeated index j is implied, and this is assumed to be spatially homogeneous. So the Hall conductivity does not depend on the I on j coordinate, and sorry all right, electric field. So this is curl, right. So the change of the curl of electric field is related to magnetic field through Faraday's law. So this is actually the EMF effect, and that we can write, and this is along the z direction, and assuming that this is x and y direction for I and j equal to all right. So what we have obtained a relations between current charge density and the change of magnetic field, and this formula is called we can even remove the time derivative and we can get a relation with small with change of magnetic field, how much the current density is changing in the system is what the Hall effect is measuring. Okay. This is a different formula, and this is only valid for the Hall conductivity, not for the longitudinal conductivity. For the Hall conductivity, it is just a measure of how much the charge density in the system is changing, in the bulk is changing due to some change of the magnetic field, and this we can convert into by multiplying the area of the entire system. We can convert this into how much charge is changing total charge is changing in the system due to change in the flux. So, A is in this case constant, so it is the change of the magnetic field. As we change the charge, as we vary the magnetic field due to EMF, we see that there is a charge that is being, so the total charge remains fixed of course in the system, but there is a flow of the charge. So, what is happening is that charge is actually moving from one side to another side, and this was the Laughlin's argument, and so this was the Laughlin's argument. So, the argument can be even visualized better by going back to that solenoid geometry. So, So, this is where the magnetic field and times some flux. So, it is rather the flux that we threaded, and let us say the system that we had, the two dimensional system, let us just use a spherical coordinate to make it called Corbino disk. So, disk geometry is the 2D material. In which the magnetic field is passing through from the center, right. So, then how do you see that? So, the amount of charge that is confined, let us say uniform charge density we had started with, and some amount of charge that was confined in this region around it, okay, some q charge that was there, and this is some area, some small area we started with, not the entire one yet, and that corresponds to some flux. And the flux is confined here in this solenoid and so on. So, now the charge, this is the number of electrons, right, this is equal to some number of electron, or I will use P times E, because charge cannot change, the total charge cannot change by any fractional value. So, it has to change by integer value. So, P must be an integer multiplied with the fundamental charge E. So, now we see that if the flux remains same, then the charge remains same. But now we are changing the flux, but the and keep the area to be fixed. So, the charge cannot just change continuously, it will only change, it will decrease or increase by only integer value. So, the electrons or the cyclotron orbit will be indifferent to the change of magnetic field until there is one charge that is removed from this area or added to this area, depends on whether the flux is along this way or the other way, or whether increasing the flux or decreasing the flux. Let us say we are increasing the flux. So, the number of let us say that we are decreasing the flux. So, and the Hall effect is positive. So, the charge should be removed from here. Okay. So, where will it go? It will go from this area to go outside. Now, there is another ring we define, and in that way also there will be charge will be somewhere here defined, but as we increase further flux it will again be removed. So, essentially in this one I had let me draw it better. So, in this region let us say, and with this much of solenoid, and in this area I had some P amount of charge, and this area I had Q P plus 1 and so on. So, in this area, as we insert one flux, one charge will go from this area to this area, and in this area is also seeing that the flux is changing. So, this in this area an electron will also go to this area, and from this area also an electron will go, and at the end the electron will be accumulated at the edge. So, what we have done is that this is one of the edge, and this is a kind of a stereographic projection of the Hall bar that we had. Okay, so, our Hall bar was like this. So, in this side we have made it this side, and this side we make it. So, this is a disc actually, hollow disc. Okay. This side is this one, this side is outer one. So, electrons are moving from inside to outside this way. So, there will be a voltage difference between this side VH, which is this voltage difference, and this will be homework to compute the angular momentum of the wave function in each ring. What you will find is that each ring will correspond to an integer value of angular momentum. So, this will be some angular momentum, then this will be the another a larger angular momentum, and so on and so forth. And as the flux is threaded through the so we talked about at the beginning of this chapter is that the angular momentum is not conserved, but angular momentum plus the flux is conserved. So, now as we increase the flux, so the angular momentum has to decrease, or depends on the sign, angular momentum can also increase. So, it is the total quantity which is conserved. So, as we insert a flux, the angular momentum increases. So, the electron has moved from one radius to a higher angular momentum radius. So, each ring would correspond to a different angular momentum. You can even define all those wave functions by going to a spherical coordinate. Okay. So, it is very clear that the flux cannot change from a electron's perspective, the flux cannot change, or the electron do not see the flux changing continuously, it is only seeing the flux changing in an integer value. So, let us say the flux is changing by integer multiplied with the flux quanta, and the charge density or charge here is changing by this much from certain area and going outside, right. And now going back to the Streda formula, so what Hall effect is measuring is for some q amount of flux threaded through the Hall bar, the p amount of electron that is pumped from inside towards the edge, and if the flux threading is changed by 1, then this is the amount of, for a integer for a 1 flux change, this is the p amount of that is electron that is being pumped from the system. So, or how many electrons that is being pumped to the edge per unit flux multiplied with this this conductivity quanta. This is the Hall conductivity that we are measuring. Okay. All right. And this charge pumping associated with this theory is called, so the charge is not conserved in this case, if you like. Of course, it's not created or destroyed, it has just been moved from one side to another side. So, in each side, if you look at, if I look into the edge, if I look into every edge state, each edge state, the charge is not conserved. And here electrons are increasing, here electrons are decreasing. So, if I look into each edge state, the charge is not conserved. So, what is happening is the charge is moving from this edge to that edge through the bulk, and bulk is insulator. That is what we have drawn, right. Bulk remains insulator, and these are the edge state, and now there are more electrons in this side from this side pumped by changing the flux. And this is called anomaly. And this theory, the way we connect it, charge density, kind of matter field and with magnetic field, this connections is the way we wrote it. This is not a solution of a Maxwell's equation, this is a solution of something called Chern-Simons theorem. It is a theory that is not gauge invariant with open boundary condition. It is gauge invariant in a periodic boundary condition, but not in open boundary condition. So, a gauge invariant theory is not a kind of a valid theory. So, what is happening is that it's to make it gauge invariant, we have to add matter fields at the boundary. So, that means the matter field or the number of charged particles are not conserved at the boundaries, and if you account for the change of that number of particles at the boundary, then the entire theory, charged particle and the gauge field, becomes gauge invariant. We will not talk about Chern-Simons theorem, but I am making a loose connections to the Chern-Simons gauge theory, which is also a topological theory. So, I hope you got a good idea about the quantum Hall effect and how that is related to quantizations of electrons around a solenoid, and the solenoid, from this quantization, solenoid can be thought of as a magnetic charge being placed at the center of the solenoid, and that can only be described by a topological manifold in which you cannot define a smooth gauge everywhere in a 3D sphere in a S2, but you need at least 2 charts or 2 gauge fields. The difference between that 2 gauge fields is a quantized quantity, and that is related to the magnetic monopole charge and the chiral phase. And with that analogy, we were also able to recast the quantum Hall effect, showing that the change of flux through the system to the quantum to a Hall bar corresponding to charge pump to the edge, and that at the edge the charge are drifted from one side to another side because of the electric field, and this is the quantum Hall effect. In the next class, we will connect these things to more of a topological invariant, which is the TKNN invariant. So, we will stop here today. Thank you for your attention.